Okay, introduction to chapter 22, inferences about means. Now we're going to do this exact same stuff that we did with means that we did with proportions in part 5. So it's the beginning of part 6. And it starts out with a discussion of how sleep-deprived high school students are, something that you all know well about. And it brings back to us the necessity of looking at the data visually. So, because we're dealing with quantitative data, we got to make a picture of the data. And just to kind of refresh your minds on that, what are the ways we can take a picture of the data? Well, we have histograms. We have dot plots. Histogram can be done by your calculator. Dot plot cannot. Stem and leaf. That must be done by hand. Box plot. That can be done by your calculator. And the normal probability plot, which can be done by your calculator. Now, these pictures are going to be used in the preconditions, one or more of them. Usually, histogram, the box plot, and normal probability plot are good to use. They can all use from the calculator to determine if the sample is big enough. So NP and NQ don't come into play here. There is no P, there is no Q. We're not dealing with proportions anymore, we're dealing with means. Okay, so the shape of the data, of the quantitative data, will be of critical importance to determining if the sample is big enough. Now, the sample mean, let's go on to the next page. The sample mean, y bar, is the sample mean. So we're talking about y bar instead of p hat. It's the sample statistic. You get your sample and you take the average from it. Okay? Now, if the mean and the standard deviation of the population are known, so if these are known, then the sampling distribution of y bar is approximately normal, mu comma sigma over the square root of n. Okay, that's if you know mu and sigma. The main thing is you got to know sigma. Okay, otherwise it would just be around y bar. Okay, so, and then this example here, if you knew mu and sigma, what would be the sampling distribution? Well, here we have for the weights of these cows, mu equals 1309 and sigma equals 157. So the standard deviation for the mean of your sample, so you take a sample from a bunch of cows. The sampling distribution, I'm sorry, the standard deviation of y bar would be 157 divided by the square root, and n equals 100. Divided by the square root of 100, which would be 15.7. Okay. All right. Moving on to the next page. Okay. Now, research on situations in which you already know the mean and standard deviation is not done very often. In fact, you're usually doing it to find that out. Okay. So, I'm going to make this a little smaller. All right, but we have a big problem that we did not have, that we don't have with proportions. Namely, the standard deviation of p hat, or the standard error of p hat, can be calculated from p hat. Namely, the square root of p hat q hat over n. Okay, but what if we don't know the standard deviation of the population? We can't make that up from either p or p hat. So, if sigma is unknown, then the standard error of y bar equals the standard deviation of the sample, referred to as lowercase italic s. Should all be happy that somehow we didn't work another p in there, over the square root of n. Okay, so the standard error of y bar is the standard deviation of the sample over the square root of n. Now, this is a nice solution to our current problem. However, it leads to a further problem. Okay, namely, we no longer are going to have a normal distribution if we're going to use this for the standard error of y bar. So this guy, a while back, this guy Gossett, working for the Guinness Brewery Company, came up with a solution, and that is there is a different sampling distribution for every sample size so the distribution for sample size 19 is not the same as the distribution for sample size 20. They're slightly different. And you say, how is this possible, or what do we do about that? Well, we'll talk about that in a little bit. Obviously, your calculator is going to handle that, okay? Now, the distribution, this is called the t distribution. You can read about all that, why it's called t distribution and everything. But know that it's called the t distribution. And instead of having a z-score, we now have a t-score instead of z-score. And which distribution you have is based on the degrees of freedom and which is simply n minus 1. So you take your sample size and subtract 1 from it, and that's the distribution that you have. That's the number of degrees of freedom that you have, and that's the t distribution. N minus 1 gives you your t distribution. That is how the percentages are going to play out. So in other words, you no longer have 68, 95, 99.7 based on your sample size. Those numbers are going to be slightly different. The smaller the sample size, the more spread out they are. And the bigger the sample size, the more it approaches normal. Okay, so t instead of z is going to equal y bar minus mu over the standard deviation of the sample divided by the square root of n. Okay, and the model, it will use the t distribution based on n minus 1. Okay, now you don't need to know where we'll talk about where those come from in a little bit. Okay, so for a confidence interval so is going to equal y bar plus or minus t star instead of z star of t star of n minus 1, whatever it is. So in other words, your levels of confidence are going to be different. The number of t's, the number of standard errors you're going to need. A t is simply a measure of standard errors, count of standard errors. Under this distribution, how many standard errors you're going to need for a particular level of confidence is going to vary based on your sample size. The smaller the sample size, the more standard errors you need to attain a certain level of confidence, times the standard error of y bar. The standard error of y bar equals the square s, the standard deviation of the sample, over the square root of n. Okay. Obviously. So anyway. So there we are so far. So we go to page 579. Let me go to the top here. That's where all that stuff is. You can go look at that again. Okay. So one sample t interval instead of z interval. So now we got a whole new thing here. Now we haven't talked about the preconditions yet. We will. A one sample t interval as opposed to a one sample z interval. Okay, so one sample t interval for the mean. All right, and so they were talking about contamination in salmon grown on farms, you know. And so they take a sample, and n equals 150, and y bar equals 0.0913, and the standard deviation from the sample is 0.0495. So you can just see the calculations here. The degrees of freedom is 150 minus 1 is 149. So we're going to use t-distribution 149, okay? And you can see the standard error of y bar is going to be s divided by the square root of n. Okay, that's pretty straightforward, 0.004. And the t star of 149 is 1.977. You can get this from the table in the back, the t tables, or from your calculator, which I will show you presently, how to get it from your calculator. Okay, so the confidence interval for y bar plus or minus t star for 149 times standard error of y bar. And we end up with a confidence interval. We are 95% confident that the mean level of Myrex constant, Myrex meaning the poison they're looking for, is between 0.0834 and 0.0992. So, all right. A lot of things are the same. A few things are different. Okay. So as n increases, the t-distribution approaches normal. Let's go on to the next page here. Let's see. Okay, now here's the calculator. So let's go through the calculator. We're not doing anything with we have TCDF instead of normal CDF. Okay? So let's play with this a little bit. Here, first I gotta pause this for a second. Okay, so we know that, here, let's get the calculator going here. Okay, so I'm going to put this over here. I'm going to clear it. So let's look at normal CDF for a minute. And I'm going to go second farthest. Now we know that, I know if I use normal CDF and I go 1.645 standard deviations, I will, in the tail, and I go 1,99, that I'm going to, I'll get to 5% significance. That's slightly under 5%. Okay. Now, I've just told you that there's going to be a different distribution for each sample size. Now, let's say I want to get to 5% significance. So let's look at, I'm going to use TCDF. I'm going to use the t-distribution. So I'm going to do second in vars, and I'm going to do TCDF number 6. And I'm going to do 1.645 standard deviations, or standard errors, let's say. And I'm going to go all the way to the end of the tail, 99, just like I did before. Now, when I'm using the t-distribution, I've got to specify the degrees of freedom, which is simply the sample size minus 1. So let's start out with a nice big sample size like we used before, a sample size of 150. Okay, so with the sample size of 150, I get very close to 5%, but not as close as with the normal distribution. Okay, but it's 0.05. It's only off by a few thousandths of a percentage points, or thousandths of decimals. Okay, so pretty close. So with the sample size of 150, but it's not the same. Okay, now let's make the sample size smaller. So I'll go to 100. Okay, so now it's a little bit bigger. So in other words, I need more standard errors to get to significance with a smaller sample than I did with a bigger sample using the t-distribution. Now in this case, it's only got to be slightly smaller. It's about, well, it looks like about 5 10,000ths or something. Okay, not very much. Okay, well, let's make it smaller still. So let's go down to 50. So I'm going to go to 50, a sample size of 50. I'll delete this. Okay, so 50. All right, now there's a pretty big difference, 3% difference. So if I have a sample size of 50 and I want to get to significance, I'm going to need more than 1.645 standard errors to do it. Okay, now let's go down to 25 and see what happens. So you can see, the smaller the sample size, the more standard errors I'm going to need in order to reach my significance. The significance isn't changing. Alpha is alpha is alpha. A p-value is a p-value is a p-value. What's changing is the number of standard errors that I need in order to reach alpha, to get down to that level. Okay? Now let's try, we'll do one more. Let's try 10. Sample size can be 10 with quantitative data. And now I'm way off, 1.5% off. Okay? So anyway, so that's TCDF. Now let's look at, we want to get T star, okay, for our confidence intervals. Okay? To do that, we use something called TCDF. I'm sorry, inverse T. All right, so let's look at that. How does inverse T work? So and this will kind of go the other way. Okay, so I'm going to do second inverse, and I'm going to do inverse T, which is number 4. Now, some of you, if you have a TI-83, you're not going to have an inverse T on your calculator. So instead, we're going to load up the program. We're going to create the program and put it on your calculator for you using the little cables and everything. We'll make sure you get started with that right away. In fact, I should work on having that ready by tomorrow. Okay, so inverse T, I'm going to put in number 4. Now, it used to be that with inverse T, with inverse norm, we put in one number. We put in whatever level of confidence we want plus however much is in the tail. In other words, you put the amount, you put in the decimal that needs to take you to the tail. All right, so we want 95%, so I'm going to put in 0.975. And then, but you have to put in a second parameter now, and that's the degrees of freedom. So, now we know that to get to 95% confidence, I need 1.96 for a 95% confidence, leaving 2.5% in the tail. Okay? So, let's put in 10 degrees of freedom and see how many standard errors I need. I know that if this were a normal distribution, I'd only need 1.96 to get a 95% confidence. I need 2.28 instead of 1.96. Now let's increase the sample size. That number should go down. So let's make it 50 and see what happens to it. Okay, a lot closer to 1.96, okay? And let's go to 100. So as the sample size increases, we get closer to the output, and now we're within a couple of hundredths of 1.96. So the distribution is, you know, we could not detect the difference in the normal distribution if we were looking at a picture of the curve between the normal distribution and degrees of freedom of 100. Now notice this is not, I said sample size 100. I misspoke myself. I should have said, or I misspoke. I should have said, you're supposed to put in degrees of freedom, not the sample size. So this, I should have put in 99. So this is what I would use if my sample size was 100. I would put in the degrees of freedom. Okay, and it's just off by a little bit. All right, so that's how those two things work, okay? And like I said, we have to get you guys with the TI-83s. We got to get you loaded up with that program, so that's something I got to work on. Okay, next page, the preconditions. Now, we talked about this already, okay? Independence, the same. Normal, the same. You need to read these over. 10%, the same. What's different? You must have a sample that is nearly normal, okay? And so that means your sample size has got to look fairly normal. Now, how do we establish that? We're going to establish that with a histogram, with a box plot to make sure we don't have outliers. Make sure it's, and with a normal probability plot to make sure that the data is approximately normal. Okay, so we will practice that as we actually have data to work on. Okay, so here's an example. Here's a histogram. Now the sample size, here's our 150 farmed salmon. The histogram is only broken up into 5 bars. It looks normal enough. Okay, it looks slightly offensive, as they tend to do. But it definitely looks normal enough. It's not bimodal. We don't have obvious outliers. We're told that it's a random sample. It's safe to assume one is independent of another. 150 is less than 10% of the population. We still got to worry about the 10%. And the histogram looks pretty good. It's slightly skewed, but it's not skewed terribly. Okay, so we're okay. That's the preconditions. All right. Now, that's it. Okay, now for homework. Here's your homework. You have to do, here's your homework, and let me write it out. And I'll put this on Edline. 1 to 12 all. These are pretty quick questions. And then 14 to 24 even. And these are calculating confidence intervals. Just use the examples. Okay, that's due tomorrow, Friday, 2:20. Okay, that's it.